Just waiting for some more people to trickle in and then we'll get started. Yep. Hello. Awesome. Yep, that's great. Yeah, so this notebook will be shared with everyone after the conclusion of the webinar. So we'll just wait just a couple more minutes to make sure that who would like to attend will attend, and then we'll get started. Hello, Manav. We will get started in about 3 minutes, just waiting for the last couple people that want to join the seminar to be able to join. Go ahead, Manav. You can type whatever question you have in the chat. No, I cannot. Okay, we'll get started in just 2 minutes. I think in this case, it may be by design. Okay, so we will get started in just 1 minute here. Yep, and as program support mentioned, so what you need to do is you need to change who you chat to all panelists and attendees, not just all panelists. Because if you put things into all panelists, only I and my lovely program support gentlemen that are on the call with me will be able to see it. Yep, there you go, Manav, that works. One other quick housekeeping thing. So I saw in our Canvas discussions that the assignment 9 solutions were missing, basically the actual solutions inside of the zip, inside of the zip file. That has been corrected as of this morning. I confirmed with the other program support people that the assignment 9 solutions zip should now contain the actual solutions inside of it. Okay, so it is 8:05, which means it is time for this webinar on decision trees. So my name is Sergi Fogelson, and I am one of the course leaders here for Applied Data Science. And so today we're going to talk about decision trees. I'm actually going to cover both kinds of decision trees in the in this webinar. So both regression and classification trees. And as I've mentioned earlier, after the conclusion of this webinar, the zip file containing this Jupyter Notebook, as well as the files needed for this Jupyter Notebook to work, will all be provided for you within the Canvas environment for this class. Also, any questions you have during the webinar, please don't hesitate to type them into the chat screen, and I will gladly answer them as quickly and as thoroughly as I can. Okay, so with that, let's talk about decision trees. So our agenda is, we'll start by talking about regression trees. I'll actually show you an example of what happens when you grow a single tree a little bit too deep. So we'll talk a little bit about overfitting with individual decision trees, and then we'll move on to classification trees, okay? Cool, so in general, so kind of the state of the art for machine learning as of today basically boils down to 2 different kinds of machine learning models. The first, this is a machine learning model that we do not cover in this course, are what are called deep neural networks, also known as deep learning, right? So those algorithms have become super popular for natural language processing tasks and for visual recognition tasks. The other kind of state-of-the-art machine learning algorithm is the batch of tree-based models. So things like random forests, gradient-boosted decision trees, XGBoost, NGBoost, CatBoost. There's a whole host of different kind of approaches to tree-based ensemble learning. That is where you have very many trees grown in some way whose predictions are all combined to yield some powerful kind of meta prediction. So these state-of-the-art machine learning algorithms are usually used on tabular data. So what I mean by that is spreadsheets, where you have rows, you have columns, and the columns can describe different dimensions of whatever the objects are that you're trying to learn from. Now, the core kind of machine learning unit of these super powerful machine learning algorithms, these ensemble methods, are individual decision trees. So in order for you to be able to understand these more powerful methods, you really need to kind of understand the stuff that's happening at the base, the kind of atomic units of these ensemble algorithms. And these atomic units are decision trees. And in fact, decision trees actually have a pretty long and successful history in machine learning and in statistical learning more generally. In fact, basically, decision trees go back to, I want to say, like the 70s and the 80s is really when they had their heyday. Individual decision trees, they were used fairly commonly in expert systems research, and they were reasonably powerful as individual kind of machine learning algorithms. They have since obviously been superseded by these more powerful ensemble methods, but that doesn't mean that they still don't serve their purposes in certain domains, and they definitely are very valuable as pedagogical tools, being able to actually understand how they work and kind of see them in action and use them ourselves. And so that's what we're going to do today. Cool. So with that, let's talk about regression trees. So the first part of today's webinar, we are going to talk about regression trees. If you'll recall, there are two different kinds of supervised machine learning approaches. One is called regression. This is where you are predicting a continuous or a real valued response. So, for example, predicting the price of a stock in dollars and cents, let's say, at the end of today's closing, predicting the lifetime value of a customer on your e-commerce platform. What else? There's lots of different examples. That's kind of, those are two kind of quick examples of regression. So you're predicting something that's not a category, you're predicting an actual value of some sort, some real value. So it has to be continuous. There's an infinite number of values that you could potentially predict from. Yeah, so that is regression. So we'll talk about that in this case. So the example data set that we're going to use here comes from the UCI machine learning repository. The data set is called the concrete slump test. The data set is actually a collection of measurements of compositional properties of concrete and their effect on the concrete's durability. Okay, so what we're going to do is we're going to use these measurements, cement, slag, or these compositional properties to try to predict one of these output measurements. So the output measurement that we're going to try to predict is 28-day compressive strength. Okay, so the idea is using this stuff to predict this value. Okay, so with that, let's get all of our imports out of the way. So these are all of the packages that we are going to be using within this webinar. So pandas, which you should now be familiar with, NumPy, which is a powerful numerical computing library in Python. And then in scikit-learn, there are several different submodules. The tree submodule, which contains the two kinds of tree decision tree algorithms that we will be using. Right now, we're going to use the decision tree regressor. Later, we will use the decision tree classifier. Then train test split, which is the method that we will be using to take our full data set and split it into training and testing sets. Then the metrics submodule, which will allow us to evaluate the quality of our trained machine learning model on unseen data. In the case of the regression problem, we're going to be using mean squared error as our error metric. Later, for the decision tree classifier, we're going to be using accuracy score as our error metric. Then for visualization, we're going to be using matplotlib. This is a magic function that allows us to actually show any graphs or charts that we have inline, that is inside of the Jupyter Notebook. And then finally, Seaborn. Within visualization, this is basically an add-on library, sits on top of matplotlib, makes our plots even more colorful, even prettier, actually gives us more plotting functionality. And then all of this here, these are actually for being able to visualize decision trees as nodes connected by edges, also directly inside of the Jupyter Notebook. Okay, so with that, ignore this deprecation warning. Don't worry about that when you run this. Basically, it's just saying that there's some packages that are going to be deprecated soon, but we won't worry about that now. We are going to be actually getting data directly off the internet. One cool piece of functionality that the read CSV function from Pandas actually has is the ability to download things directly off the internet if the data set is tabular and can be ingested directly off the internet. So I'll show you. If you take this hyperlink and you put it into a URL, you'll see that it actually just downloads the hyperlink directly to my computer. So what I've done is I've simply put that hyperlink as my input string into read CSV, and it automatically converts it into a data frame. I've also passed in this parameter index call, set it equal to the integer 0, because the very first column is the index into every single row in this data frame. And so having done that, we now have our data frame stored inside of this cement data variable. What I've also done here is I've actually changed the column names a little bit. I have lowercase the column names, and if you'll notice, I've also replaced the spaces with underscores, periods with empty strings, so just removed the periods, removed the left and right brackets, and have also replaced dashes with underscores as well. And so now what you'll see is when you do head here, we have nice clean names for all of our columns, which means that we can now directly access them using dot notation. If you'll recall, there are two different ways to access individual column names in Pandas. One is with dot notation, another is with bracket notation, in the way that you would access, for example, keys in dictionaries. This will allow us to access individual columns using dot notation. This renaming, I mean. Okay, so now, as I mentioned earlier, we're going to be using a machine learning model, our decision tree regressor, to predict this last column using all of these columns. So the first 1, 2, 3, 4, 5, 6, 7 columns. Okay. So what I'm also going to do is, in order to actually visualize the compressive strength column visually, what I'm going to do is I'm going to create a new column that remaps the compressive strength into bins of equal size, starting from a bin that has the smallest compressive strengths up to a bin that has the largest compressive strengths. And I'm going to make them go in kind of a blue to red color scheme. So blue means lower compressive strength value bins. Red means higher compressive strength value bins. And so I'm going to do that using this cut functionality. Okay, so what I've done here is I've created my X matrix, my Y vector. My X matrix just contains the first 7 columns. My Y vector contains just the very last column in cement data, which is this column. So I have my feature names, I have my target name, and then finally I'm going to create this compressive strength bins column using pd.cut, 5 equally placed created bins. And now, what you should see here in a second is a pair plot that visualizes all of these basically relationships and color codes everything according to the compressive strength bins. So now what you can see here, so take a look here, I've zoomed in. So you can see that there's 5 different compressive strengths, and instead of the actual value, what we've done is we've relabeled all of the points with the respective bins that they fall into. So this point, for example, means that it falls into the 33 to 41, I'm sorry, 33.7 to 42 compressive strength bin. A dark red, for example, this point falls into the 50 to 58 compressive strength, and then a dark blue like this falls into the 17 to 25.5 compressive strength, okay? Along the main diagonal, you have the histogram of each of our features, okay? And then along each off diagonal is basically a scatter plot for each pair of features and all of the basically points that fall on those features, colored by their corresponding compressive strengths, okay? And so we can see that some of these actually have pretty reasonable separability. In fact, take a look at this, scatter plot. You can see that actually the more blue data points and the more red data points actually are reasonably well segregated from each other, okay? So what I've actually done is I've actually created this one right here. So this is fly ash and cement. I've actually created this scatter plot as its own larger scatter plot. So take a look at that here, okay? Now, what we're gonna do is we ourselves are actually going to create a decision tree without actually using the decision tree algorithm. And I'll show you how we're gonna do that, okay? We're gonna do it using just these two features, okay? And so we're gonna build basically a decision tree model that can actually give reasonable predictions for compressive strength. And we're gonna do it as follows. I'm actually gonna need your help here, all right? Cool. So this is the way that we're gonna have to do this together, okay? You can only use straight vertical or horizontal lines to segment the space, okay? The vertical or horizontal lines must always stop as soon as they meet another vertical or horizontal line. So as soon as you draw a given vertical or horizontal line, the very first one that you draw, for example, will fully bisect the space in some way, right? But after that, any new vertical or horizontal line that you draw, as soon as it comes across another line, it must stop there. It can't continue on. And finally, the way it will work is as soon as we create a region, some region, like you can think of it as like a little box, what will happen is our prediction that we make for the compressive strength will simply be the average of whatever the values of the points are in that box. Now, the problem is we don't actually know what those numbers are. All we have are the colors. So our goal is going to be to make the colors within each of our boxes, our little box areas, as uniform as possible, okay? So the goal is make it so that the boxes are small enough such that the colors of all of the points in those boxes are as uniform as possible. And you can make as many lines, vertical or horizontal lines, as you want, okay? Okay, so with that, please tell me, where should we make our very first either horizontal or vertical line? I want you guys to type that into the chat. So given this, okay, horizontal at 50, perfect. Okay, so let me write that down, okay? So horizontal at 50. And then I'm gonna listen to you Mao. After that, what I'm going to do is I'm going to ask you, you said vertical at 175. So now that we have a horizontal line at 50, do you want the vertical line to be above the horizontal line or below the horizontal line? You want it below, so you want it to go like this. Okay, that's fine. So vertical at 175 below the horizontal line. All right. Where should we put one next? So right now we basically have one line here and another line right here. So now we have one big space here, a little space here, and another space here. I suggest that we put one more vertical line somewhere. Any idea where we can put, so we have one horizontal line here, one vertical line that does this. Any more? I think we should put a vertical line somewhere in this area. Vertical at 225. Perfect. So that's about right here. So let's just stop there. So right there. Okay, awesome. So vertical at 225 above the horizontal line. Okay, cool. So I'm actually going to, well, let's just stop there for the sake of time and for the sake of explanation. And I am actually going to label these regions. So let me actually do this. Let me go to, or actually, no, not preview. What should I do? Well, no, that's fine. So I'm just going to stop sharing my this screen, and I'm just going to share my full screen. Or 1 second, hold on. So let me, sorry guys, just 1 second. Let me do this. So now that we have these, so horizontal at 50. The question is the amount of fly ash greater than or equal to 50? So greater than or equal to 50 is up here, less than or equal to 50 is down here. If it's greater than or equal to 50, then is the amount of cement greater than or equal to, you said 225. So what I'm going to do is I'm going to label the regions very quickly. So we've created, I know you have to keep this picture in your mind. We have one horizontal line here, one vertical line here, and another vertical line here, okay? So what I'm going to do is I'm going to call these different regions. I'm going to call this region 1. I'm going to call this region 2. I'm going to call this region 3. And I'm going to call this region 4, okay? So is the amount of fly ash greater than or equal to 50? Greater than or equal to 50 puts us into either region 1 or 2. It puts us somewhere up here. If the answer is yes, right, that's what we said yes is, then the next question we will ask is the 225 question, right up here, okay? Is the amount of cement greater than or equal to 225? If yes, then that puts us into region 2. Okay, then take the average of region 2, else, so if no, then take the average of region 1. That's the average of whatever these values are here, okay? So if the amount of fly ash is less than 50, then, right, so it's less than 50, then if the amount of cement is greater than or equal to 175, then take the average of region 4. If no, take the average of region 3, okay? So this is a decision tree. What we just did by drawing our one horizontal line here and our two vertical lines, is we've actually created a simple two-level decision tree. That's literally what we just did, okay? Now, what a machine learning algorithm that uses decision trees does, or that uses the decision tree approach does, is it automatically does what we just did using some very basic heuristics. We'll talk about what those heuristics are in just a second, but for now, I just want to show you how the decision tree constructs it very rapidly and show you the resulting decision tree that is made. But it's going to basically look very, very similar to what we just created here, okay? Okay, so we're gonna do that by building our model on 60% of the data and evaluating it on 40% of the data. So that's what we've done here. We have our train test split. We're taking our X and our Y, splitting into 60 and 40. We're setting a random state so that all of us have the same exact train test splits. And so now you will see, so we've instantiate our decision tree, then we fit it with our training set, then we evaluate it with our test set. And what I've done is I've actually computed the root mean squared error. I use the root mean squared error because it's at the same units as the original data, which is a little bit easier to interpret than the mean squared error. But they basically come out to the same thing, okay? So here, you'll see that the RMSE is about 5.3. So on average, we're gonna be off by about 5.3 units, which isn't really that bad. I mean, it's not great, but it's not super bad when our range is between 17 and 58. Also notice that I set the maximum depth to 2, which means that we're gonna have basically 2 questions that we ask in order at most along a single line of questions on the decision tree. And you'll see what that looks like here. So here's how I visualize the decision tree. And now you can see the questions that are actually being asked. And so here is the question. The very first question that is asked is the amount of cement less than or equal to 160.1? So the first question that the decision tree here asked is actually vertical, and it's right about here, okay? If the answer is true, then the next question that is asked is the amount of fly ash less than or equal to 136.5? Less than 136.5 is right about here, so that is the cutoff. So that means that it's created this as its own region, okay? And so the average of the values in that region is right here, 21.24, okay? If the answer is no, so if it's false, then the average actually becomes the values up here, okay? It becomes the average of the values up here, which is right around 32.4, okay? Now, if, however, the amount of cement is greater than 160.1, which puts us into this side of the space, right? Then we ask, is the amount of fly ash less than or equal to 115.5, okay? And if it is less than 115.5, then again, we take the average of these values in this general area, which is right around 32, 31.9. And then if it's not the case, if it's false, then it puts us into this region, okay? And in this region, the average compressive strength is 43.6, okay? So that's exactly the decision tree that that scikit-learn automatically created using the training set. Now realize that the training set doesn't contain all of the data points that we just visualized here. It actually only contains about 60%, some 60% randomly chosen points found here, okay? Notice also, I showed you that there's only 4 different regions, which means that there's only ever going to be 4 distinct values that the decision tree will predict, okay? There will be a distinct value for this region, another one for this region, another one for this region, and another one for this region. And we can confirm that by looking at the actual unique values that the decision tree predicts on the test set. And they are exactly the 4 values found in the leaves of the decision tree. They are these exact values, okay? You can see that here. Cool. All right, so if you kind of look at this, you can see, and here's another interesting point here. I only showed you these 2 features, but the decision tree actually used all of the features in the training set. There were other features included in the training set. However, with a depth 2 decision tree, the decision tree algorithm picked up on the fact that all of the other features didn't provide nearly as much information as FlyAsh and Cement did for constructing a depth 2 decision tree. So it effectively completely ignored all of the other features. They were just completely ignored. Okay? So what this tells us is that for a depth 2 decision tree, the only features that are worth anything for building this model are Cement and FlyAsh. Okay? The relative contribution here of Cement and FlyAsh is a little bit difficult to evaluate from just building the tree, because although Cement is at the top of the tree, which suggests to me that it's the most important feature, FlyAsh is used in both sides of the depth 1 questions that are being asked, which means that it could be the case that FlyAsh actually winds up being more important in terms of explaining the reduction in error in the decision tree than Cement itself, even though the Cement question is the first question that's being asked, okay? Okay, so how does a computer actually build a regression tree? So in the ideal case, what it could do is it could try to consider every possible partition of the feature space. It could literally go through for each feature and see how the total reduction in error happens as you basically segment on each possible cut point. So you can try to segment here, try to segment here, try to segment here, all the way through across every possible Cement segmentation, all the way through across every possible FlyAsh segmentation. And each time you segment into smaller regions, you look at how that kind of average prediction of the entire region space reduces the total error in your prediction, and then pick the one that is the best. However, the problem with that ideal approach is that it will take a prohibitively long time, okay? So a good enough approach is what's called recursive binary splitting. So what that does is for every feature, you examine every possible cut point and choose the feature and cut point such that the resulting tree has the lowest possible MSE, okay? So that when you split things into the regions, you have the lowest possible mean squared error following that specific split. You can see that in these cases here. The MSE at the very beginning is just the difference between the average prediction across all of these points relative to the actual prediction for all of the points. You can see that the MSE at the very top of the tree is very high, but as you split and go down, the MSE actually decreases, right? So you can see that goes from 55 to 26, and then from 26 to 11, or from 26 to 14. Here it goes from 115 to 10, and from 115 to about 18.9, right? So what you do is, for every feature, you only imagine every possible cut point, and then you freeze the decisions for those features. You never go back up, basically, and test new cut points. You just keep shrinking the new resulting regions by finding smaller and smaller areas that reduce the MSE as much as possible, okay? And you keep repeating this previous step until you meet what's called a stopping criterion. And that stopping criterion can be one of two things. The first is that the maximum tree depth has been reached. That is, the maximum number of splits required to arrive at a leaf is reached. In our case, that maximum depth was 2, and so that was our stopping criterion. The other stopping criterion is that that you reach a point where there's a very small number of observations left within a specific leaf. In the most extreme case, you can't have fewer than one observation in a given leaf, in a given little box, basically. You can imagine a leaf as a box that contains a certain number of samples. In our case here, this box only contains 3 samples, all right? In the case of the training set. If we were to try to break this box down further, it might only contain, one side might only contain 1, another side might only contain 2. As soon as you have a box with only 1 sample, you can't break it down any further. So in that case, you're forced to stop the building of the decision tree at that specific level, okay? So that's the other, basically, stopping criteria, okay? But there are other good reasons to stop growing a decision tree beyond some just arbitrarily deep level. And I'll show you that here, okay? So here what I'm showing you is the training and the test set RMSE as we grow our decision tree to an arbitrarily deep depth, okay? So what I've done here is I've created a decision tree with depths ranging between 1 and 10, okay? And I'm showing you, comparing the training set RMSE to the test set RMSE. And what you'll see is that although the training data set error goes down effectively to 0, the testing set RMSE is actually, right, it's actually doesn't keep going down. It actually flatlines around 3, and then it slowly creeps back up. You see how it slowly creeps back up. What this whole area tells us is we've effectively overfit our decision tree, okay? We are now basically fitting noise. We're not learning anything useful, okay? So what that means is this is the place where we want to stop our training. We want to only train it to a depth of about 3, and then use this point as our ideal, as our best decision tree, okay? And you can see what that decision tree looks like here, all right? And you can see that now, in this case, when we grow it to depth of 3, we start using other features. We start using water, slag, and SP, okay? And you can look at the feature importances, okay, and see in this case that the basically the feature importance allows us to see overall, on average, which feature is the most versus least important. And we'll see that in this case, the most important feature is actually water, which accounts for 50% of the total reduction in error, followed by cement, which accounts for about 38% of the reduction in error, followed by water, which accounts for about 9% of the reduction in error, and then slag and SP, which account for between 1 and 2% of the reduction in error. And then finally, coarse agar and fine agar are not used in the decision tree at all, which you can see here. It's not used there at all. And as a result, they do not reduce the error at all. Okay? Okay, cool. And then finally, you can make predictions on the testing data in the same exact way that we make predictions on any new data from other machine learning algorithms using the scikit-learn API. We simply call the predict method on our fitted decision tree and pass in our testing data set, and there are our predictions. Yes, Richard. So feature importance is a function that you call. It's right here. So actually show it to you. Once you fit a individual decision tree, you can call feature importances, and it gives you the feature importances in the same order as the features arise in the training set. So this is cement, this is slag, this is fly ash, this is water, this is SP, and then this is coarse and fine agar. Yep. Okay, cool. So we talked about this. So now these last 15 minutes, I know we're running a little bit out of time, or running a little bit behind. I just want to quickly mention how you can do the same exact thing using classification trees, okay? The big difference between I've given you an example of a classification tree. This was actually a decision tree that the New York Times built to try to predict which of either Obama or Clinton was going to take a specific county using demographic information from that specific county. Okay, so we can actually compare basically the difference between classification and regression trees. So with regression trees, what you're doing is you're predicting a continuous response. With classification trees, you're predicting a categorical response. In the example of the Obama-Clinton primary county predictor, the output is a prediction on whether Obama or whether Clinton will win a specific county. The input is a bunch of demographic information about that county. Okay? Okay, cool. So so the output for a regression tree in the leaves is the basically the mean of the samples that fall into a specific leaf, into a specific terminal node in the decision tree. For a classification tree, what you actually do is you just predict the majority vote that falls into a specific leaf. So if, for example, a specific leaf has 5 examples falling into it, 3 of them say Obama, 2 of them say Clinton, then the prediction in that leaf is going to be Obama. Okay. Now, lastly, the big difference between classification and regression trees is that with regression trees, your splits, the way that you choose splits, is to minimize the maximize the total reduction in MSE. So you want to minimize the overall MSE that you see as a result of making a split. But with classification trees, splits are actually chosen to minimize what's called the Gini index, okay? And so the Gini index, or the Gini impurity, is a measure of how often a randomly chosen element from a given set of elements would be incorrectly labeled if it were randomly labeled according to the distribution of labels in the subset. Okay, basically the idea with Gini impurity is you are trying to make it so that all of the samples post-split are as uniform as possible within a specific region of the space as possible. So that's the whole goal. As opposed to minimizing the MSE, what you're trying to do is you're maximizing the uniformity of the labels within a region post-cut, okay? So that's the way to think about it. Maximizing uniformity, okay? Which is the same as actually maximizing Gini impurity. So I actually have examples for both of these things. So an example of the classification error rate and an example of the Gini impurity, and I go through the math of how this is done, okay? I'm not gonna talk about it because we are running a little bit out of time. So what I suggest is, if you're interested in how this works, the examples that I have here, if you load up the Jupyter Notebook, you can work through it and you can see how exactly either classification error rate or Gini impurity can be used when you're trying to figure out which features to split something on in a decision tree. The beautiful thing about scikit-learn is you don't actually have to worry about any of this. Scikit-learn automatically uses this to be able to find the kind of the ideal places to split things when you're building your classification algorithm. In general, Gini impurity is actually preferred over classification error rate because it will make splits that increase node purity, even if that split does not change the classification error rate. And node purity, so the amount of the uniformity of the samples found in a terminal leaf or in a region of space, is important because we're interested in class proportions in each region, since that's how you can actually calculate not just the class prediction, but the predicted probability of a given class given some terminal or leaf node prediction. Okay, because with decision trees, just like with logistic regression, you actually get a prediction probability. You don't just get a classification, a label, you actually get the prediction probability. Okay, so with that, let's actually quickly build a classification tree. So we're going to be using some room occupancy data that was published at the UCI machine learning repository. The data set is a collection of sensor readings within a given room and manually validated occupancy checks within that room at 1 minute intervals. So that means if the room was occupied, the occupancy value within that 1 minute interval is 1. If it wasn't occupied during a given 1 minute interval, the occupancy value is 0. So that's what we're going to try to predict. So take a look here. We have actually separate training and testing data sets already. So we can load them in separately. And that means that we don't actually have to split our data. It's already split for us. The data that we have is we have the date of the reading. We have a temperature reading every minute, a humidity reading, a light reading, a CO2 reading, a humidity ratio reading, and then the target is whether it was occupied or not. So occupancy is binary. It's either 1 or 0. Okay. So we are going to use temperature, humidity, light, CO2, and humidity ratio as our input features. We're actually going to ignore the date as an input feature. Then we have our training and testing sets. We already said that we had created those. Now we have our classifier. And finally, we train our classifier on the training set, which we had created up here below. And then we test it on our testing set, and we can see that our accuracy is actually fairly high. It's 98%. And if you'll recall from our decision tree homework notebook, the actual kind of the majority class probability is actually only 64%. So this means that we are actually able to capture some meaningful information, right? Because our accuracy is significantly higher than the majority class frequency, we know we're actually able to predict with above chance accuracy the occupancy of the given 1 minute interval. So if we visualize this data set, we can now see that what we're actually basically capturing is a combination of light, humidity, and CO2 measurements. And then there's one little case of temperature. But light overwhelmingly dominates the questions that we ask, so we can expect light to be super important. And that is exactly the case in the case of this classification tree. Notice that light accounts for, the light value accounts for almost 99% of the reduction in the the Gini impurity or the Gini coefficient over the entire decision tree. Basically, what we've done is we've created a light detector. What our machine learning algorithm has done is it's basically saying if the light's on, somebody's probably in the room. If the light's not on, somebody's probably not in the room, which isn't really that interesting, right? Needless to say, it still can capture with pretty high accuracy the occupancy of a given room within a given 1 minute. Okay. Great question, Richard. That's a good point. I don't know. I'm not sure. Clearly, temperature. Oh, right. Great question, Mal. So that is the overall fraction of positive and negative examples. So in the earlier case, it's a great question. In the case of the the regression tree, darker colors mean higher values, lighter colors mean lower values. The colors here mean closer to red means that the frequency of positive examples is higher, so true values is higher. And then bluer values mean the frequency of false or zero values is higher. So notice the distribution here. You have 24 ones, 1,400 zeros, right? 56 ones, 233 zeros. And then here it's the opposite. Here it's 6,000 ones, 2 zeros, 155 ones, 5 zeros. So it's just the class frequency. So higher class 1 frequency red, higher class 0 frequency more blue. Okay. So I just want to finish this up by comparing decision trees with other machine learning models. So there are some clear advantages to decision trees. They can be used both for regression and classification. They can be displayed graphically, which is awesome. I mean, that's not something you can normally say for logistic regression. You can sort of say that for linear regression because you can write out the full linear regression model. But I think a decision tree is a very clear, I think it's a very intuitive way to describe a decision process for some task. Okay, they're obviously very highly interpretable because you can understand exactly how the decision tree algorithm is making the choices it's making at specific points. They can be basically commodified. They can be converted into a series of rules, and they can, as a result, more closely approximate human decision making than other models. Their prediction is fast. You don't need to scale the features at all. You can just throw all of the data as it is into the decision tree model and it'll just work. It also automatically learns feature interactions, and that's because decision trees are fundamentally non-linear models, which is not the case with linear regression and logistic regression. And they tend to ignore irrelevant features. We saw that with both of these cases, right? It basically throws out features, doesn't even bother to use features in the decision tree model that don't provide any predictive power. And because they are nonlinear models, they will outperform linear models if the relationship between features and response is highly nonlinear. So that means that even in the case of linear and logistic regression, a decision tree in certain cases will outperform their performance, okay? However, decision tree performance is generally not competitive with the best supervised learning methods. So what I mean by that is they are not nearly competitive with the ensemble methods that I talked about at the very beginning of class. An ensemble of decision trees, such as a random forest or a gradient boosted decision tree model, will almost always, like 99 or 999 out of 1,000 times, will outperform a individual decision tree, okay? Furthermore, as I showed you earlier, in the case when we grew our regression tree too deep, they can easily overfit the training data. So a substantial amount of tuning is required. You need to be very careful about making sure that you do not overfit the decision tree to the training set. Finally, small amounts of variations in the data can result in completely different trees. If we had done a slightly different split in our training data, it is very possible that we would have gotten a very different decision tree as a result of the way that we selected our training data set. So it's very sensitive to the training data. This is what's called a high bias learner, okay? This is a problem. And then finally, decision trees, they tend to not work well if the classes are highly imbalanced, or if you have a very small data set that you're training your decision tree on, okay? But again, to conclude, it doesn't mean that decision trees aren't a valuable pedagogical tools, and it doesn't mean that they aren't valuable or useful models in certain cases. I've actually come across cases where a decision tree model used on a small data set is much more informative than a much fancier model, because it clearly shows to people the decision making that is behind the algorithm, okay? So with that, this is kind of the conclusion of the webinar. I hope this was useful and allows you to understand a little bit about how decision tree models work. And yeah, and again, I will post this resulting collection of files to our Canvas within the next few hours. This has also been recorded to the cloud, so you can review this. Webinar in your own time. Thank you very much, Richard. Thank all of you. Thank you all very much for joining me this morning. And please do come to my webinar also next week, where I will actually explore clustering models. So I'll have a webinar at this same exact time. So it's scheduled for 8 a.m. Eastern or 1 p.m. UTC next Tuesday, where I talk about clustering models. Okay? All right. Enjoy the rest of your weeks. Take care. Have a great day. Bye-bye. All right. So I'll post this to our Canvas shortly. Thank you, guys. Thank you for your help.